Here you are. I think we're good to go. I'm not muted or anything, am I? Okay. Absolute convergence and the ratio and root tests. All right, so let's talk about defining absolute convergence. So given any series, sigma an, we can consider the corresponding series, sigma absolute value an. And that's just if we took the absolute value of each term and added them together. And we call a series absolutely convergent if the absolute values converge. Okay. So for example, if we look at this series, this is an alternating series. It's not the harmonic series, but it's kind of the alternating harmonic series squared. And so the terms are 1, and then minus 1 over 2 squared, and then plus 1 over 3 squared, and so on and so forth. And if we look at the absolute value of that series, so sigma absolute value of negative 1 to the n minus 1 over n squared, well, all the absolute value is going to do is take away this alternating. It's going to eliminate the alternating portion, right? So now the numerator no longer alternates between negative and positive 1. Instead, all terms would be positive, so this just equals sigma 1 over n squared. Now, is sigma 1 over n squared convergent? Yeah. And if so, can you give me a proper justification? Good. Convergent. And it would be P series with P equals 2, which is greater than 1. And so then I can say, therefore, sigma negative 1 to the n minus 1 over n squared is absolutely convergent. All right. Why is that useful? We'll get to it. Slow down. We know that the alternating harmonic series is convergent. Okay, we proved that using the alternating series test. But if I look at the absolute value of it, that's just going to equal the regular harmonic series. And what do we know about the regular harmonic series? Just 1 over n. It's divergent. And again, we can just cite P series. But in this case, P equals 1. And if P is less than or equals to 1, it's going to diverge. Hey. So, yeah, have a seat wherever. All right, so the alternating harmonic series converges, but the absolute value doesn't converge. So it's convergent, but it's not absolutely convergent, right? What do we call that? That's called conditionally convergent. Oops. Good. So absolute convergence and conditional convergence have some properties that are pretty interesting. Specifically, conditionally convergent is very strange. And we'll get to that at the end. But the reason we want this is that we will know that if a series is absolutely convergent, then it's also convergent. Meaning if its absolute value converges, then the original series must converge as well. And I'll kind of walk you through the logic of this proof. I just want to give you a chance to write down the actual theorem. All right, the proof may look a little complicated. It's really not, and it's pretty clever. So let's think about this statement. Say I have the sequence AN. It has to be true that AN plus the absolute value of AN has to be between 0 and 2 times the absolute value of AN. If AN is positive, say AN equals 3, then what you have is 3 plus 3, which is 6, and then 2 times that is 6, and that inequality holds, right? 6 is between 0 and 6, as long as we have the or equal to sign there, yeah? Does that make sense? What if AN was negative 3? Well, then you'd go the other way. You'd have negative 3 plus the absolute value of negative 3, which would be positive 3. That would give you 0. And 0, again, is between 0 and 6, as long as we have the inclusive or equal to, right? So either way, this sum has to be between these two values. All right, so now let's look at the corresponding series. If sigma AN is absolutely convergent, then that means, by definition, that this series is convergent. That's the definition of absolutely convergent, right? So if you have a convergent series, if you just multiply it by 2, it's still going to be convergent, right? Convergent just means adds up to a finite number. So if you have something that adds up to a finite number, if you multiply that 2, that doesn't make it infinite, it just makes it 2 times that finite number, right? So sigma 2AN has to be convergent. And so then what we're saying is that sigma AN plus absolute value AN has to be in between sigma 0, which is definitely convergent, you're just adding up zeros, and between sigma 2AN, which we just said is convergent. And therefore, by the comparison test, that middle one has to be convergent, right? If this is finite, and this is finite, finite, then the sum between has to be finite, right? It's a comparison theorem, very similar to the squeeze theorem in like Calc 1. All right. And so now we can do a little math to isolate sigma AN. So sigma an equals sigma an plus the absolute value an minus sigma absolute value an. And that's just because these would cancel each other out, right? And we already proved that this is convergent and this is convergent. And so if you have two convergent series, you have something that adds up to a finite number minus something that adds up to a finite number. That's going to be finite as well. Therefore, sigma an itself must be convergent. And we've proven that if your function is your series is absolutely convergent, then the corresponding series without the absolute value must also be convergent. All right, so why is that helpful? Determine whether this series is convergent or divergent. All right, well, for this, we're going to use the comparison test. The problem is the cosine in the numerator. What is cosine going to oscillate between? It's a wave. 1 and -1. So there are values that will make that cosine negative, right? All right, but if I look at the absolute value, that's going to guarantee that my cosine is always going to be less than what? 1, but greater than 0. Meaning this has to be strictly less than sigma 1 over n squared, doesn't it? Because the biggest the numerator will ever get is 1. And the denominator is the exact same. So I can say, therefore, before I make that statement, let's state this converges, right? Because it's a P series. Where P is equal to 2, which is bigger than 1. All right, well, if cosine's always positive but less than that, therefore, sigma absolute value cosine n over n squared has to converge by comparison. And now we can say that sigma, the original one, cosine n over n squared, is absolutely convergent. Therefore, convergent, which is what we proved in that last theorem. If the absolute value converges, then the original series has to converge as well.
So, like in terms of using this in relation to like the alternate series test, isn't this always going to be more helpful?
Yeah, if you can prove, yes. So if you can prove, but the problem is, what about the alternating harmonic series? If I asked you for convergence of that one, the absolute value of that wouldn't converge because the absolute value of that is the harmonic series, and the harmonic series is divergent, right? But the alternating harmonic series does converge, and the way we show that is by the alternating series test.
So it's like, something where like you can only prove that it is convergent, but if it doesn't pass, it's like.
Yep.
Okay.
It's exactly. And this one you're generally going to use kind of in conjunction with some other theorem, like we did here with the comparison test or something like that. All right. So from this, we can develop this thing called the ratio test. In the ratio test, you're going to look at the infinite limit as n approaches infinity of a sub n plus 1 over a sub n. So you're looking at the corresponding sequence. And if that gives you some constant L, and L is less than 1, then the series is absolutely convergent and therefore convergent. That gives you some value L that's greater than 1, then the series is divergent. If it gives you a value equal to 1, no conclusion. Got to figure out a different way. Okay. So we're just going to follow this formula and test this series for absolute convergence. And what we want to look at is just the corresponding sequence, an, which is the negative 1 to the n without the sigma, right? N cubed over 3 to the n. And at that point, I want to use the ratio test, which is taking the ratio of absolute value of a sub n plus 1 over a sub n. All right, so this is going to be absolute value. I'm just replacing all my n's with n plus 1. It's going to look kind of nasty at first, but it simplifies down pretty quickly. Negative 1 to the n plus 1 times n plus 1 to the third over 3 to the n plus 1. And that's going to be divided by a to the n, so just negative 1 to the n times n cubed over 3 to the n. All right, well, first of all, taking the absolute value is just going to completely eliminate this negative 1 to the n and negative 1 to the n plus 1, because all those do is alternate between negative and positive 1, depending on what term you're at. But the absolute value is just going to make them always positive. Okay? So now we can just focus on the n plus 1 cubed over 3 to the n plus 1 divided by n cubed over 3 to the n. And I can drop the absolute value at this point because n is just the index of my term in the sequence, so n is always positive. All right, so this becomes n plus 1 cubed over 3 to the n plus 1, and then I'm going to change this to multiplication of 3 to the n over n cubed. Okay. So n plus 1 cubed times 3 to the n. Now we have this little trick. You add exponents like we did here, when you have a product of powers. So I can use that in reverse. I can rewrite 3 to the n plus 1 as 3 to the n times 3, right? And now that gives me a factor of 3 to the n in the numerator and in the denominator, and those will divide each other out. All right, so now let's look at this. We have, I'm going to write it as 1/3 times n plus 1 cubed over n cubed. Well, since those are both cubed, I can just rewrite this as 1/3 times the quantity, n plus 1 over n quantity cubed. And then finally, I can just divide n into both those terms inside parentheses. I get 1/3 times n divided by n is 1 plus 1 over n to the third. All right, so remember, that's the ratio of the absolute value of n, a sub n plus 1 over a sub n. And now what I want to do is take the limit as n goes to infinity. Well, we only have one term with n here. If we let n go to infinity, what does 1 over n approach? 0, right? So this is gone. That's 0. I have 1/3 times 1 plus 0 cubed, which is 1/3, yeah? And the ratio test said that if that specific ratio comes out to less than some value less than 1, then your series is absolutely convergent, therefore convergent. If it's greater than 1, it's divergent. If it equals 1, you got to find another test to use. Inconclusive. Yes. Yeah, exactly. So all this says to do is replace the n's with n plus 1s. So I replaced all the n's in my original sequence with n plus 1. And that's this right here, right? It's just the original a sub n. Exactly. All right, so we want to make our conclusion is less than 1. Therefore, sigma, I'm just going to call it sigma an, is convergent. You don't have to cite all the different tests that went into this. Just now cite by the ratio test. Because this is just n plus 1 divided by n, right? So n plus 1 divided by n equals n divided by n plus 1 divided by n. And then that simplifies to 1 plus 1 over n, right? I mean, you can do that. That's the same thing. If I divide the numerator by n and denominator by n, it'll get me to the same place. All right. Ooh, here's a weird one. Sigma n to the n over n factorial. You guys remember what factorial is? So like 4 factorial equals, or if you wish, 1 times 2 times 3 times 4. Sometimes it benefits you to think of it in the opposite direction. But it's just the product of whole numbers down to 1. All right. So we're going to use the same thing. Let's go ahead and use the ratio test. So a sub n is just the corresponding sequence without the sigma, so n to the n over n factorial. And so then absolute value of a sub n plus 1 over a sub n will be, all right, the numerator, we just need to replace all the n's with n plus 1s. We'll have n plus 1 to the n plus 1 over n plus 1 factorial. All right, so that's my a sub n plus 1, and then here's my a sub n, just n to the n over n factorial. Okay. Now, absolute value doesn't really do anything here. All these terms are already going to be positive, so we can just drop that immediately. But then I'm going to flip, since this is a complex fraction, we're going to flip and multiply, right? So over n plus 1 factorial times n factorial over n to the n. All right, couple little tricky things that we can do. So 4 factorial is 4 times 3 times 2 times 1. Isn't that the same as 4 times 3 factorial? So n plus 1 factorial, isn't that just n plus 1 times n factorial? By the same logic? So I'm just using this logic. 4 factorial is 4 times 3 factorial. So n plus 1 is 1 bigger than n, right? So then n plus 1 factorial is just n plus 1 times n factorial. All right, so let's do this. I'm going to do one thing at a time here. So n plus 1 times the quantity n factorial, and then I have n factorial over n to the n. All right, that gets rid of my factorial, right? Now again, n plus 1 to the power of n plus 1, can't I just rewrite that using the product of power rules as n plus 1 to the n times n plus 1? Do you agree that's the same as n plus 1 to the n plus 1? All right, so that helps a little bit because now we get rid of those n plus 1 terms. And now we're left with n plus 1 to the n over n to the n. All right, again, these are both to the nth power. So I can rewrite it as just one fraction all to the n. So that's n plus 1 over n quantity to the n. And again, I can just divide that n into both terms in the parentheses and rewrite this as 1 plus 1 over n, and that's all to the n power. All right, so once I've got it simplified, then I'm ready to take my limit as n approaches infinity. But this one we run into a little issue. What does my 1 over n go to? 0. But n, that exponent, is going to be infinite, and so I end up with this 1 to the infinity, which is what we call an indeterminate form. This is actually a really, really famous limit. And so we can handle this, I think, and it's not too bad. Here's what I'm going to do. I'm going to let y equal that limit as n goes to infinity of 1 plus 1 over n to the n. Now, when you have a variable exponent and you're trying to deal with that, a great tool for that is taking the log of both sides, because basically logarithms are the inverse of exponentials, right? So I'm going to go ahead and take natural log of both sides of this equation. So I'll say that ln y equals limit as n goes to infinity of ln 1 plus 1 over n to the n. And that opens up properties of natural log, one of which is if I have an exponent on my argument, I'm allowed to bring it down as a coefficient on the logarithm, right? So now I can bring that n down and say, okay, ln y equals limit as n goes to infinity of n times 1 plus, oh, whoops, forgot my natural log, apologies, of n times natural log of 1 plus 1 over n. This is still an indeterminate form, because if you try to evaluate this, n goes to infinity, this is going to go to 0, so you're going to have natural log of 1, which is 0. Infinity times 0 is not necessarily 0. It's indeterminate. All right, so one more way I can rewrite this. I'm going to rewrite that product as a quotient and say that this is the same as natural log 1 plus 1 over n over 1 over n. All right. And now, again, the numerator is going to go to 0. The denominator is going to go to 0. You do have an indeterminate form, but guess what? This is an indeterminate form that we can use L'Hopital's rule for. All right, this is kind of, all right. I'm really realizing this is a little messier than I thought it was going to be in my head, but we're almost at the end. So L'Hopital's rule just says take the derivative of the numerator, take the derivative of the denominator, and then reevaluate the limit. Natural log of a function, you take the derivative of the inside and you put it over the inside function. So the derivative of the inside is going to be, derivative of 1 is 0. Derivative of 1 over n is going to be negative 1 over n squared, and that's over the original inside function, so 1 plus 1 over n. Great. And then derivative of the denominator is just negative 1 over n squared. Okay. Well, to speed this process up, notice that these negative 1 over n squareds are going to be canceling each other out. And I'm just going to be left with basically 1 plus 1 over n. Sorry, it's going to be 1 over 1 plus 1 over n. All right, now if I evaluate my limit, finally ready to go. What does that limit approach? 1. Now, that's not the limit we were looking for, because remember, we were looking for y, and this is actually the limit natural log y. So how do I undo y? I have ln y equals 1. I'm going to exponentiate by e. I get y equals e. So our true limit is e. So this is actually a quite famous limit. To get back to what we were actually looking for, it's in this step. That limit right there that I circled is the definition of e. All right, so our ratio came out to e. So this equals e. Which that was our original ratio. That was equivalent to absolute value a sub n plus 1 over a sub n. So what does the ratio test tell us about this? What is e approximately? Right. Well, I thought it would be interesting. This part wasn't part of the example. Like, it was just assumed that you knew that, but I didn't think you guys knew it. So I was like, hey, we can prove this real quick, that this is the definition of E. And then I got to it and I was like, okay, this is a lot of unnecessary algebra. But it's fine. That is, now you know that's the definition of E. And since E is greater than 1, this is divergent. I'm going to say, therefore, sigma a sub n is divergent by the ratio test. All right, something that kind of is derived from the ratio test is another one, and it's called the root test. It's pretty similar, but it involves still looking at the infinite limit, but now you're taking the nth root of the absolute value of your corresponding sequence. And then the parameters are the same. If that comes out to a value less than 1, then the series is convergent. If it comes out to a value greater than 1, then the series is divergent, and if it's equal 1, the test is inconclusive. It's pretty obvious when you want to use the root test, because you're going to have something to the nth power, and you want to figure out a way to get rid of the nth power. This gives you a way to get rid of the nth power. All right. So you use it the same way. It's just a slightly different test. Instead of taking the absolute value of a ratio, you're taking the absolute value of the nth root. And like I said, it'll be pretty clear to use because you'll be looking at something like this, where your entire corresponding sequence is being raised to the nth power. All right. So same idea. I'm just going to say, all right, so a to the n is just equal to the corresponding sequence 2n plus 3 over 3n plus 2 to the nth power. And so then, applying the root test, I want to look at the nth root of the absolute value of a sub n. Now, in our case here, the absolute value isn't going to do anything. 2 times n plus 3 over 3 times n plus 2. That's always going to be positive. We don't have any like negative 1 to the n's that are making our series alternate or doing anything like that. So the absolute value doesn't do anything there. But taking the nth root is going to cancel out our nth power. So this is just going to leave us with 2n plus 3 over 3n plus 2, right? All right, And then, again, the ratio test just says we want to look at what's going on as n approaches infinity. So once we've kind of simplified after taking the nth root of your corresponding absolute value sequence, then we're going to take the limit as n goes to infinity of 2n plus 3 over 3n plus 2. Now this is a situation where we have a ratio and we have multiple terms in the numerator and denominator versus like a single term in the denominator. So we're going to want to take the more traditional approach where we divide the numerator and denominator by the highest power of our variable in the denominator. So what would I be dividing by? Not just 1, but what's our variable? So just n to the first power. So I'm just dividing by n and dividing by n. Which, yes, I'm overall dividing by 1. That's the point, right? We're not actually changing anything. We're just rewriting this in a way where it's easier to evaluate an infinite limit. Okay, then 2n, if I divide that by n, 2, and then I'll get plus 3 over n over 3 plus 2 over n. And then as n approaches infinity, 3 over n goes to 0, 2 over n goes to 0. Our constants stay constant, right? And this evaluates to 2/3. All right, so what does the root test tell us? Convergent. So I'm going to just say, therefore, sigma an converges by the root test. Okay, so that's the ratio test and the root test. And we talked about absolutely convergent versus conditionally convergent. And we said that if a series is absolutely convergent, then it's also convergent without the absolute value. But I said there was some weird stuff about conditional convergence, and I want to talk about that for a second because it's pretty interesting. Let's look at the alternating harmonic series. So we'll do negative sigma negative 1 to the n minus 1 over n from n equals 1 to infinity. And we did prove that this converges. We used the alternating series test last time to show this, right? So this is just the series that goes 1 minus a half plus a third minus a fourth plus a fifth and so on. And it is convergent, but it's only conditionally convergent. Because we just saw that if we take the absolute value and try and find the convergence, it doesn't work. Well, Ramadinajad, Indian mathematician, proved that this converges to natural log 2. So 1 minus a half plus a third minus a fourth plus a fifth. And I'm going to do a few terms just because I'm going to minus a sixth plus and so on. Actually comes out to natural log 2. We proved that it's convergent, but we didn't find the sum. And you could do this. In a normal year, I would have taught you some estimation theorems that we skipped over in a couple of these sections, just because I want you to be exposed to as many of these convergence tests as possible. But there is an exercise in 11.3 where you actually show by mathematical induction, which we also learned about, that this is true. So this is the part where I just need you to accept that this is true. It is convergent. We already proved that. And I'm telling you its sum is natural log 2. But it's conditionally convergent. So I said that conditionally convergent stuff can do kind of weird stuff. All right, so what if I multiply both sides by 1/2? This is an equation, so that's allowed, right? It's a property of equality. I'm allowed to just multiply both sides by the same constant and still maintain equivalence. All right, well, my terms would become 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12, and so on, right? And then that would have to equal natural log, or sorry, 1/2 natural log 2. All right. Well, I should be allowed to insert as many zeros as I want without changing the sum of the series. Does everybody agree with that? So if I add in 0, and then I'll do plus 1/2, plus 0, and then minus 1/4, plus 0, and then plus 1/6, and then plus 0, and then minus 1/8, and so on. That should still just equal 1/2 natural log 2. If all I did was add in zeros, right? Now, what I want to do, there's another property of equations that says if you add two equations that are true, you maintain a true equation, right? Like you learned in algebra that you can use that property to solve systems of equations by elimination. You get their coefficients to be the same but opposite, and then you add them, and you maintain equality. So I should be able to add this equation to my first equation, so to this without the multiple of 1/2, okay? So I'm going to add that to basically 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. And that one equals just natural log 2. Well, on the right-hand side, I'm going to end up with 3/2 natural log 2. On the left-hand side, I'm going to end up with 1. Those 1/2s cancel, so plus 1/3. Negative 1/4 plus negative 1/4 is what? Nope. It's negative 1/2. Plus 1/5. You end up here, you're going to end up with 2 negative 1/8. So it's going to be actually negative 2/8. That's going to be minus 1/4. And so what you'll notice is that this series actually has the exact same terms as our original series. They're rearranged though. So I have the 1, I got the 1. I got the negative 1/2, I got the negative 1/2. I got the 1/3, I got the 1/3. Got the negative 1/4, 1/4, 1/5, 1/5. And so we end up with the exact same series, but the terms are rearranged. And what do you notice about the right-hand side of this series with the rearranged terms versus the original series? They're different. Even though they're the exact same terms, one adds up to natural log 2, the other adds up to 3/2 natural log 2, right? So conditionally convergent series are weird. You can rearrange the terms, and you can actually get it to add up to any number you like. So they are convergent, but the order of the terms matters, which is bizarre. They're conditionally convergent, meaning the order in which they're added is the condition on what they converge to. So Bernard Riemann actually proved that you can do this. You can rearrange the terms to be add up to any real number you like. All right. That's what we got for today. There is a problem set 11.6 that is posted, and I've also